Yeah, let's talk about that. You mentioned that earlier. What the heck is mathematics? And
Okay, so okay. So what is mathematics? Mathematics, sort of at a lowest level, one thinks of mathematics as you have certain axioms. You say things like x plus y is the same as y plus x. That's an axiom about addition. And then you say we got these axioms, and from these axioms we derive all these theorems that fill up the literature of mathematics. The activity of mathematicians is to derive all these theorems. Actually, the axioms of mathematics are very small. You can fit, when I did my new kind of science book, I fit all of the standard axioms of mathematics on basically a page and a half. It's not much stuff. It's like a very simple rule from which all of mathematics arises. The way it works, though, is a little different from the way things work in sort of a computation, because in mathematics, what you're interested in is a proof. And the proof says, from here, you can use, from this expression, for example, you can use these axioms to get to this other expression. So that proves these two things are equal. Okay, so we can begin to see how this is going to work. What happen is there are paths in metamathematical space. So what happens is each two different ways to look at it. You can just look at it as mathematical expressions, or you can look at it as mathematical statements, postulates, or something. But either way, you think of these things, and they are connected by these axioms. So in other words, you have some fact, you have some expression, you apply this axiom, you get some other expression. And in general, given some expression, there may be many possible different expressions you can get. You basically build up a multi-way graph. Mm-hmm. And a proof is a path through the multi-way graph that goes from one thing to another thing. The path tells you how did you get from one thing to the other thing. It's the story of how you got from this to that. The theorem is the thing at one end is equal to the thing at the other end. The proof is the path you go down to get from one thing to the other.
You mentioned that Gödel's incompleteness theorem is not natural. It fits naturally there. How does it fit?
So what happens there is that the Gödel's theorem is basically saying that there are paths of infinite length. That is, that there's no upper bound. If you know these two things, you say, I'm trying to get from here to here. How long do I have to go? You say, well, I've looked at all the paths of length 10. Somebody says, that's not good enough. That path might be of length 1 billion. And there's no upper bound on how long that path is. And that's what leads to the incompleteness theorem. So, I mean, the thing that is kind of an emerging idea is you can start asking, what's the analog of Einstein's equations in metamathematical space? Mm-hmm. What's the analog of a black hole in metamathematical space?
What's the hope? So, yeah, it's fascinating to model all the mathematics in this way.
So here's what it is. This is mathematics in bulk. So human mathematicians have made a few million theorems. They've published a few million theorems. But imagine the infinite future of mathematics. Apply something to mathematics that mathematics likes to apply to other things. Take a limit. What is the limit of the infinite future of mathematics? What does it look like? What is the continuum limit of mathematics? What is as you just fill in more and more and more theorems, what does it look like? What does it do? What kinds of conclusions can you make? So, for example, one thing I've just been doing is taking Euclid. So Euclid, very impressive. He had 10 axioms. He derived 465 theorems. Mm-hmm. Okay. His book, that was the sort of defining book of mathematics for 2,000 years. Mm-hmm. So you can actually map out, and I actually did this 20 years ago, but I've done it more seriously now. You can map out the theorem dependency of those 465 theorems. So from the axioms, you grow this graph, it's actually a multi-way graph, of how all these theorems get proved from other theorems. And so you can ask questions about, you can ask things like, what's the hardest theorem in Euclid? The answer is the hardest theorem is that there are 5 Platonic solids. That turns out to be the hardest theorem in Euclid. That's actually his last theorem in all his books. That's the final.
What's the hardness? The distance you have to travel?
Yeah, it's 33 steps from the longest path in the graph is 33 steps. So that's there's a 33-step path you have to follow to go from the axioms, according to Euclid's proofs, to the statement there are 5 Platonic solids. So okay. So then the question is, what does it mean if you have this map? Okay, so In a sense, this meta-mathematical space is the infrastructural space of all possible theorems that you could prove in mathematics. That's the geometry of meta-mathematics. There's also the geography of mathematics. That is, where did people choose to live in space? And that's what, for example, in exploring the sort of empirical meta-mathematics of Euclid
you
is
could
doing
put
that.
each individual, like, human mathematician, you can embed them into that space. I mean, they kind of live
they represent a path in
the little
space,
path,
the things they do.
maybe a set of paths.
Right.